So, as Sina said, my presentation will be about toughening of bonded interfaces in composite joints and how we can use this to upgrade green materials, or which is more sustainable materials. So the presentation will be divided in two parts. One which will be focused on the scientific work that we've been performing in the last 5 to 7 years on toughening of bonded interface, and the second part more focused on how can we upgrade sustainable materials, mainly polymers. So the motivation. So, I mean, you're doing a master in composite structure, so there is a reason for that. So composites have been increasing their share in many infrastructures, both in energy infrastructures, in automotive, and aerospace has been one of the leading in implementing composites in infrastructures, but also more recently in traditionally more heavily structures, such as shipbuilding and civil engineering. And as you may know, these structures are not made of one single piece. They're made of different pieces that need to be assembled together. And one of the most efficient ways of joining, so they have interfaces either between composites and composites, or composites and metals, or any other type of material. But one of the most efficient ways to join these interfaces is using bonding, which are adhesively bonded structures, in which you use a polymer, which is called adhesive, that connects the both structures together in one line of polymer. So why is this very efficient? Well, in comparison, of course, with rivets or mechanical fasteners, because rivets and mechanical fasteners, once you drill a hole on the composite, you're cutting the fibers, the main loading carrying capacity of the composite, which are the fibers, and you are decreasing enormously the performance of the substrate. Therefore, it kind of fits the purpose of using composites, because you are using composites to improve the efficiency, and then you drill a hole on it and you decrease their efficiency. However, applying bonded joints, it doesn't come without challenges. Well, the first main challenge is that you need to know what you're doing when you apply a bonded joint. While in rivets and fasteners, it's easier manufacturing, so you just need to drill a hole and put a rivet on it. For bonded joints, you need to have a really good quality control of the manufacturing. So you need to know which surface treatment you need to use for the substrates, which adhesive is the best to use for the specific application. So the quality of the manufacturing is crucial for having a high quality of a bonded joint. This is crucial for having a good joint. Another challenging is that there is nowadays interface failure is undetectable. It is quite unpredictable. What is an interface failure? An interface failure is what we generally call a kissing bond, which means that the polymer, so you have the two substrates and the polymer are joined together. So in looking at it, observing just by visual eye, everything seems to be integral and no defects. However, when you start to detach both surfaces, there is no really strength on it. So there's a contamination in the surface, for example, or there is something that went wrong on the quality on the manufacturing, and that creates an interface failure. This interface failure the strength is much lower. It is much more susceptible to any type of environmental conditions, degradation. So it must be avoided. It must not be in infrastructures, but it's undetectable with our current NDT techniques, non-destructive techniques, such as ultrasonic, C-scans. They cannot detect this type of bonded joints. So this is a huge limitation for applying bonded joints in full-scale primary structures. And one of another challenges is the limited crack arresting capability of a bonded joint. What does this mean? It means that once you have a crack on the bond line, the crack can propagate very suddenly, can have a catastrophic failure of the joint, because there's nothing that stops the crack from growing. And I would like to give you an example of it. So here is two specimens of a bonded joint. So this area here is the bond the bonded area, the overlap area. And these are fatigue tests. This one has 2 rivets here drilled in the composite, in the bond line, and this one doesn't have any rivets. So this is a test performed by Airbus in a European project called BOPAX, and these are the results. So what we see here is the graph you see here is the delta A, which is the increasing of the crack length. So how does the crack propagate for the number of cycles, number of fatigue cycles. So you see here that once you have, for the adhesive, plain adhesive, we have a sudden increase, exponential increase of the crack growth. While when you have the adhesive plus the fasteners, the crack grows in a much more stable manner. So the rivets can hold and arrest the crack. And this is why in current primary load bearing structures or primary structures, the certification does not allow to have only bonded joints. It must be a bonded joint with some kind of design feature that can arrest the crack. And this has to do also with the monitoring of the structures. So if you have a monitoring of every X number of flights, for example, in an aircraft, between those X number of flights, you must be able to detect if there is any catastrophic damage to the structure. So if the crack grows very fast, you might not be on time. So this is why it's very important to have crack arresting capabilities. However, the rivets are not by far the most optimal design feature to arrest the crack, because as I said before, they cut the fibers of the composite, they create high stress concentrations. So you need to double almost the amount of, double or more, the amount of material that you have to put on composite in order to withstand the stress concentrations that come from the rivets. So in this presentation, I would like to focus on trying to find solutions for this last challenge. So improving the crack arresting capabilities of bonded joints without using the rivets. So without having any damage a priori to the composite. And this is what we call toughening mechanisms to increase damage tolerance of bonded joints. So I will be exposing some of the things that we have been doing, trying to target this challenge. But before that, I also would like to give you a little bit of a background on toughening mechanisms and energy release rate, because I'm not sure what is the background that you have on fracture. So in my presentation, you will see a lot in several slides, this graph. And this graph gives you the energy release rates against the crack advance. What is this? Well, the energy release rate is the energy necessary in order to break a material into 2 parts. So in order to open a fracture surface. And normally this material is, it's a property, it's discussable in the scientific community, but let's say it like that for now. It has a critical energy release rate, which is a property of the material that it's the energy in joules, so it's energy, that it's necessary to open a crack in that material per unit area, per square meter. So this is generally seen as a material property, but it can be modified depending on the geometry that you give to the material. And I'll give you a very simple example that you probably use every day, which is in the toilet paper. So if you have a toilet paper without, and if you try to tear it apart without, not in the region where you have the perforated line, you know that it's very difficult, because the material, the toilet paper in this case, has a certain critical energy. So how can we make the crack advance easier? We then make a modification in the geometry of the material, in this case, a perforated line, that it makes our life much easier, because you can easily remove the toilet paper, and it actually decreases the critical energy release rates of the toilet paper, and it creates a preferable fracture surface. That's the place where we want the fracture to grow, the crack to grow. So we can apply this simple example also in structures. Well, as you can imagine, we normally in structures don't want to decrease the energy release rate. We want to increase the energy release rate. So that's what we try to do. And in literature, there's many things that we can do it for polymers. So we want to improve this energy that it's necessary to to fracture the material. So we can include, for example, in the polymer, thermoplastic thermoplastic inclusions or nanoparticle inclusions that can improve the critical energy release rate of the material. But we can also add crack arresting features, which means that once the crack advances, the energy necessary for the crack to open increases every time the crack advances. While in the blue line, we see that once it reaches the critical energy, the energy is always the same, meaning that whatever crack advances, the energy necessary to open the crack is always the same. However, in the red line, every crack advance, you need more energy to open the crack. So this is the ideal solution, because every time the crack is advancing, we are arresting the crack. So for this one, there is also many examples in literature, but I just keep here two, in which we create bridging mechanisms between the two substrates, either created by a mesh which is incorporated in the adhesive, either a polymer mesh or a copper mesh. And by creating these bridges between the two substrates behind the crack tip, we can arrest the crack even further. So this gives you a little bit of an example of what are toughening mechanisms and how can we tune the material properties, either by geometry or by changing the material properties in itself, to improve the energy release rate. Now, now I will focus more on what we have been doing for composite to adhesive bonded joints. And I divided the presentation in two parts. One in which we focus in tuning or increasing the toughening mechanisms by using composites. So by changing the property of the composite itself, which is a substrate, and another one which is changing the properties of the adhesive. And I will start first with the composites. And the first parameter that we tried to change was the ply thickness. So here you see overlap, a single lap bonded joint, which was tested in tensile load. Here you see the schematic. Here you see the test in itself, the specimen, with the DIC patterning speckle. And what we varied was the ply thickness. What does this mean? So we called the specimen which was thick, in which we had a 200 microns ply thickness. And then we decreased the ply thickness to 100 microns and 50 microns. So as you can see, these are images all with the same scale. And you see that there is a decrease on the ply of each ply of the composite. One ply is here, the second one only this one or this one, and on the third one is even thinner. So in this one we had 50 microns of ply thickness, which is considered an ultra thin composite. In order to focus, in order to have only the parameter of ply thickness to interpreted results, we had to maintain most of the other parameters that we know also influence the damage constant, such as the bending stiffness of the composite was always the same. The position of the first 0 degrees layer, which also has an influence on the damage on the crack propagation, which was always in the second ply. And the ply, which is in contact with the adhesive, was also always 45 degrees angle. So these parameters to be constant are very important in order to, so that we don't, we know that we are only focused on the ply thickness for determining the results. So these are the first results, and what I'm showing you here is the fracture surfaces. So once we broke the specimen, we looked to the surfaces where the fracture occurred. They normally give you a lot of information about what happened. So here for the thick, for the medium, and for the thin. What we first see that it's pretty clear is that almost everything is black, which means that the crack propagated mostly in the composite. The adhesive that we had was a pink adhesive, AF163-2, which is commonly used in aircraft structures. You see a little bit of adhesive there, a little bit there and there, but most of it is only composite failure. What we also see is that if we look to the fracture surface in comparison with the overlap area, where the area where we had the bone line, for the thick, this area kind of propagated further than the bone line. And as we decrease the thickness, the fracture surface was more contained only inside the adhesive layer, the region of the adhesive layer. So we had a 20% decrease in the delamination area when we decrease the thickness. If we have a closer look into the fracture surface, so now what we see here is a 3D profilometer of the fracture surface, so we have a topography of the surface. For the thick, we see that the fracture surface mostly traveled within the first and the second layer, so always within the 45 degrees angle or in between these two. But the crack didn't travel a lot within the composite, so it was quite flat. So this is a cross section of the specimen. And when we look to the same, when we make the same exercise, but now for the thin, we see that we have a quite different fracture surface. So the crack traveled between the interface 9 and 10, 6 and 7, first and second. So there was a lot of steps within the fracture surface that the crack traveled during the damage scenario. So this was quite different from the previous one. Now, in order to try to understand better why is this happening, why we have on the thick only one quite flat crack path, and here we had a stepwise crack path. For that, we performed a finite element analysis to try to understand where is the crack initiating. So here what we see is a closer a zoom in of this region here of the bonded joint, so closer to the edge and the fillet, which is normally the hot spots where the stress concentrations happen. And on this scale here, we see the failure index. So blue, it means that the node is far from failing, and red, closer to 1, it means that the node is close to failure. So we applied here a failure criteria in the composite in order to understand how close were the stresses to failure. So for the thick one, what we see here is that the hotspot, so the first node to fail, is the one closest to the adhesive, and it's quite isolated. So there is some also here, but most of it is concentrated here on the adhesive. Now, if we look to the same geometry of the adhesive, but now we have thin plies. So we had much more plies in the substrates. What we see is that the hotspot, the stress concentrations, move away from this area, and they concentrate more in the region through the composite ply thickness. So we have, first of all, we have more points, not only one isolated, but more points in which the stresses are concentrated, and they are also further deeper into the composite. So what does it tell you? So when we compare with the fracture surface that we had, how does this match? Well, I think it matches pretty well, because for the thick, we have one single matrix crack at the interface ply angle, which matches pretty well with what we've seen about the one flat fracture surface for the thick that we've seen in the profilometer. And for the thin, we see several matrix cracking throughout the composite stiffness on the verge of fracture. So what does it mean is that when we decrease the ply thickness, we create more regions where the crack, where the material is being used and it's getting closer to failure. So there is a crack competition between these different areas of the material. And because there is this crack competition, once there is a crack, might be simultaneous or might be between different, within very close time frame. So they happen at the same time. And then they coalesce between each other. So this is why in the thin, we see more steps in the fracture surface, as we saw here, because they happen at different locations and then the coalescence all together. So what is the result of this different fracture mechanisms for the thick and for the thin in terms of damage resistance of the bonded joint, which is what we wanted to see. So when we go from the thick to the thin, we see that there is a change of crack locus. So the crack started at different locations. And when we use thin, there is a crack competition between different areas of the material. What is the result of this? The outcomes are that the damage initiation is postponed by 50% when we use thin, and the final failure is also postponed by 15%. So we actually managed, just by changing the ply thickness of the composite, to increase the damage resistance or the damage initiation of the damage resistance of the bonded joint. So this was for the ply thickness. Now, if we change the layup design, so as you know, composites are made of different plies in different directions, in different angles. So we try to see how is the influence of these angles in the fracture behavior. And for that, we used what we call a double cantilever beam test, which is mostly under opening mode. So the bonded joint is under opening, which we call mode 1 fracture surface. And we see how the fracture propagates from the beginning, which is here, until the end of the specimen. And we changed the layup, so we used all 0 degrees as reference, a cross ply laminate, and a more non-conventional laminate using 90 and 60 degrees plies. And we also used 2 different adhesives. A very tough adhesive, which has 2,000 joules per square meter, and a low toughness adhesive, which is about 500 joules per square meter. And to check what was the influence also of the fracture toughness of the bond line. So these are the first results. What you see here is again this graph that I was showing in the beginning of the presentation. So here is the energy release rate against the crack length. So this is the reference specimen. So all 0 degrees ply. And what we see is that the crack propagates always inside adhesive. So you have a complete pink fracture surface. So there is no sign of fracture in the composite. When we have the cross ply, the 0,90,90, we see a very different fracture surface. So we see a little bit of adhesive here, but then the crack deflects to the composite, and it delaminates once it reaches the 0 degrees, the 0 degrees. When we look to the energy that it's necessary to grow the crack in the specimen, we see that there is a increase in the damage in the resistance to damage in the initiation, but at the beginning there is a little bit of increase, but once the crack advances a bit further, there is a huge decrease because of the delamination in the composite. Now we try to understand, so we didn't understand this because the delamination in composite, it's known to be very, very weak. It's out of plane properties, but we didn't understand exactly why was this increase in the damage initiation resistance. So we tried to look a little bit more into our pictures for the microscope that we were looking at the test. And what we saw was that in the beginning, we see a little bit of damage nucleation in the adhesive. And then we see 2 types of cracks. A primary crack, which is in the adhesive, but we also see a secondary crack, which is in the 90 degrees matrix cracking inside the composite. So because we have these 2 cracks happening at the same time in the joint, we again trigger this crack competition between the 2. So the energy that we are imposing in the specimen is being divided between 2 fracture surfaces. one in the adhesive and another in the composite. And this is why we see this increase in the fracture energy. So that was explained. Now, if we use, so this was for the high toughness adhesive, the very 2 joules per square meter adhesive. Now, if we do exactly the same task and the same substrate, but now with the low toughness adhesive, what we see is that for both specimens that we were seeing before, both for the 0 and for the cross ply, we have 100% cohesive failure. Because the toughness of the adhesive is lower, it is the preferred crack path. It's easier for the crack to grow inside the adhesive than deflecting inside the composite. However, when we look to the non-conventional laminate, so with 90 and 60, what we see here in the energy is that we have an increase, significant increase in the energy in the beginning, and then we see again a low energy at the end. So looking at the fracture surface, what we see is 100% composite failure. We don't see any adhesive. And so we try to understand why did we have this increase in the damage area in the beginning. And what we saw was, so what we did was a C-scan. So we use, no, not a C-scan, sorry, a CT scan, which is a computed tomography X-ray, which we use X-rays in order to visualize better what is inside the specimen. And this is what we saw. So here you see the adhesive is the lighter area, and here is the crack that it's propagating inside the composite. And indeed, what we see is that you see a lot of crack fronts. You see a crack front here, you see a crack front there, you see a crack front there and there. So there is a lot of crack deflections and a lot of fracture surface that we're opening at this location. And because it's all compete with each other and they all distribute the crack energy, the energy that we are imposing to the specimen, they decrease the crack length. So this is why we have an increase in the beginning of the specimen. At the end, once it reaches a certain plateau, a certain crack, and the crack is always the same, then you see the delamination that we also saw before. So indeed, what we learned is that if we have a lot of fracture surfaces, so if we manage to dissipate the energy that we are imposing in the specimen to several fracture surfaces and several crack fronts, we can indeed increase the energy that is necessary to increase a crack. So what are the outcomes of this sub-study that we have to perform? So crack competition and crack deflection between the cohesive failure and CFRP layout led to an increase of 25 to 90% of the crack resistance of the joint, because indeed the energy is being spent in different locations, and it can outperform the onset damage initiation of the cohesive failure. And the composite layout plus adhesive properties can be tuned or architected to increase the fracture toughness of the CFRP. So the combination of changing the composite layout and with the adhesive properties, we could increase the fracture toughness of the CFRP. So this was for the composites. I will now focus on what we've done to modify the adhesive fracture toughness. And first, looking to microstructures. What are these microstructures that I'm talking about? These microstructures are kind of a mesh that is embedded in the polymer, in the adhesive. As you see here, in this case, it's a 2D carrier. That once we open the fracture, what we see is that this nylon mesh creates bridging mechanisms between the two substrates. So you see here, it looks like a spider web in the region of the fracture surface. So what is the consequence of this in the fracture resistance? What we see here is that we have, again, the same graph that I was mentioning to you. So the fracture toughness against the energy release rate against the crack line. And what we see, so we had to look closer to also to the X-ray CT, and you see all these nylon fibers connecting the two substrates. in a significant amount of locations within the adhesive. So because they create this bridging between the two substrates, what we see is that we have an increasing in the fracture toughness, the energy release rate. And as you remember, this is exactly what we wanted with the fracture toughness, that every time we increase the crack, the energy necessary to increase further the crack is even greater. So this is great. However, this happened only by chance, because this nylon carrier was not put there to do the crack bridging. It's there just for manufacturing purpose. So this is just by pure luck that we saw this phenomenon. But it kind of triggers us to try to use this phenomena in our advantage and control the phenomena without being only for luck. So what we saw with these microstructures is that these lattice microstructures embedded in adhesive could trigger the bridging phenomena, and we could increase 2 times the resistance to fracture of the adhesive. So this is very promising. Now we can also do something with the adhesion patterning. And the adhesion patterning is adding some contaminations in the surface. So using a defect, which where I was talking with you in the beginning, the kissing bond. So this is the contamination area of the adhesive. And try to see, can this be used in our favor to toughen the adhesive? So what we did was putting some contamination strips. And here you can see the fracture surface. So you see the crack growing inside the adhesive, then shifting from the adhesive to the interface. And then again, once the defect was over, we shifted from the interface back to the cohesive. So by changing this crack locus and using this, we saw what was a phenomenon that was coming afterwards. And this was inspiration for future work. In what they did, this is work done by Chaos University in Saudi Arabia by Professor Jules Loubenou, in which they used exactly this interface failure in order to create different crack fronts. So they used kissing bonds or low interface strength, and they deviated between each other. So they kind of not on top of each other, but they intercalated. And by doing that, they created adhesive bridging, adhesive ligaments, and created different crack fronts. By doing that, so here you see the different interface regions and the ligaments that have been done to arrest the crack front. So here you see a similar phenomenon. We have more than one fracture surface and more than one crack tip location. And if we plot the energy release rates against the crack length, we see that indeed there is an increase from 0.72 up to 1 kilojoules per square meter using these bridging mechanisms of using the adhesive and the interface patterning. So not always a defect can work against us. We can also use it to architect the material and the interface. And finally, the adhesive layer geometry. So what can we do in the geometry of the adhesive to create toughening mechanisms? And this was a work that was performed for very thick bone lines for shipbuilding industry or for wind turbine blades. In these industries, we have quite thick bone lines. So in aerospace, we have about maximum 1 millimeter. Here we are talking about 1 order of magnitude higher, 1 centimeter or even further. So here you see the same type of test, the double cantilever beam, in which we open a part, but now with the 10 millimeter thick bone line. And you see that the crack propagates in different regions within the adhesive. And this was one that propagated like that, but others propagated in a different way in a different crack path. So by creating these very thick bone lines, what we create is also not only, so normally we would only have 1 stress concentration, which would be here in the crack tip, 1 singularity. But by creating these thick bond lines, we create two extra singularities. So this region here and this region here also has stress concentrations because it has different materials and due to the geometry. So what we saw is that for a certain delta A, which was the initial crack length, sometimes we had a crack onset close to the interface. Sometimes we had a crack onset at the middle of the adhesive thickness. So it means that at certain points, sometimes this was predominant, and at other times this was predominant. And you can also see this in the finite element analysis that we performed. So if we have, and this is this gain between either here or there, it's what we found out is it's mostly, and it's quite understandable, that it's related with this delta A. So for delta A's which are smaller, the stress concentration is not enough here and the crack deviates to the interface. If the delta A here is longer enough, then these regions here lose their stress concentrations and this becomes the predominant crack tip. And we can see also that in the finite element analysis that we performed, in two extreme, here I show two extreme cases, here without any crack, any initial crack length, in which you see indeed that the strains are higher at the interfaces. And after a certain delta A, which we call delta A critical, the stresses are no longer predominant here, but the crack will propagate here at the crack tip. And by doing the tests, we found out a geometrical relationship, which is this relationship, which depends on the thickness of the adhesive and on the thickness of the adherent. So we can actually control where the crack is going by changing this delta A. So in fact, it's similar to the toilet paper case study, in which we changed the geometry, we perforated the geometry in order to lead the crack path into the place where we want it to go. Now, if you think about this in a further step, it does mean that if we change the geometry of the bond line, we can actually say where the crack will be growing. So we can rely more on the geometry of the bond line rather than on the material properties. So if you think about this in a bigger scale, you can have metamaterials in an adhesive bond line. Because in this case, with the metamaterials, the geometry is the key factor for the crack propagation. And you can play with different geometries to tune the crack path and create different, many types, several crack deflections, several fracture surfaces in order to increase the fracture resistance. So as we saw, this toughening mechanism, so increasing the energy that is necessary to increase the crack, to further grow the crack, it's a combination of both the geometry of the bond line and the material properties. So please keep this in mind for the conclusions of the presentation. So now I would just like to briefly, so how does this connect with green materials and bio-based adhesives? So I would just like to show you a little bit of the work that we've been doing in bio-based adhesives. So most common epoxies that we use in infrastructures, they contain BPA. And BPA is one of the, I think one of the chemical components that it's mostly produced in the world. It's petroleum-based and it's toxical chemical component. All of the epoxy that we were using for CFRP, for adhesives, they have BPA. Ideally, we would like to get rid of it. So what we did was trying to replace the BPA by tannic acid. And tannic acid is a component that it's bio-based, coming from, for example, grapes. And we tried to see if we could, with this modification, we could get rid of the BPA or what was the consequences of replacing this BPA by tannic acid. And we performed the same type of tests, the DCB, with aluminium and CFRP. And here is an example of the energy release rate against the crank length and the fracture surface. what we see is that we have both cohesive failure and adhesive failure. But even when we have cohesive failure for different types of combinations of the tannic acid, we got a maximum energy release rate of 150 to 200 joules per square meter. This, if you remember, is 1 order of magnitude lower from the one we were using to the aerospace structures, which was 2000 joules per square meter. So with these properties, bio-based adhesives, which have BPA-free, they have a very low fracture energy, and they also have poor adhesion. So these bio-based adhesives, they have an inherent poor mechanical properties. So there is no way with these properties that they can be applied in load-bearing infrastructures, because they simply cannot compete. It's too low. So how do I aim to help these bio-based materials? By upgrading them. Well, if you remember from what I've been talking about in the last 40-45 minutes, by changing the composite ply thickness and the composite layout, we could outperform the onset, the damage initiation of the cohesive failure, and we could postpone 50% the damage onset. And this change in the fracture resistance was without changing anything in the material properties of the adhesive. When we look to the adhesive, by adding a mesh inside the adhesive, we could double the fracture resistance. By adding adhesive ligament, we could also outperform the interface failure. And by changing the layer geometry, we could also tune the crack locus and crack path location. In none of this toughening mechanisms, I've changed the mechanical properties intrinsic of the adhesive. I only added different geometries or different substrates that could change the fracture resistance. So this is my last slide, and what I want to leave you with is for the future, if we rely more on geometry and less on the mechanical properties of the material, we could then replace the current full-based epoxy resins by bio-based epoxy resins, which have lower mechanical property, which could be compensated by the geometry that we place into the resin or to the adhesive. And this is actually already what it's done in nature. Materials which are coming from nature, they have a very low intrinsic mechanical properties, but they are built up in such a way, they're architected in such a way that at the end, they have very high toughness and very high resistance. So this is what we also need to change, in my vision, to get bio-based materials inside our structures. So by doing that, I believe we can improve the mechanical performance of bio-based adhesives and implement them in high load-bearing structures. So this is what I had to share today. Of course, all this work was not performed by me, so I have many people who I have to thank within my department and in my group. And of course, I'm open to any questions that you might have. Thank you.